So you taught us that effective atomic number rule was done.
Metal carbonate.
Yes,
Yes,
sir.
yes.
Okay. So the existence of the metal carbonyl depends on whether the metal carbonyl satisfies the effective atomic number rule, except in one case, that vanadium hexacarbonyl, which is an exception where it does not satisfy the effective atomic number rule, but it exists. Did I mention that?
Yes, yes, sir.
Now, did I mention that if the metal carbonyl is short of 1 or 2 electrons from effective atomic number, then it can attain the effective atomic number one way by accepting electrons that you have seen. That it can accept 1 or 2 electrons to satisfy the effective atomic number. Is it?
Yes.
But
Yes.
there is another way of satisfying the effective atomic number. Suppose it is short of 1 electron, like MnCO5. MnCO5 has 35 electrons. It is 1 short of 36. So,
Yes.
it can form a metal-metal bond and forms a dimer. In that case, the manganese 25, manganese atomic number is 25. That means 25 electrons are there,
Yes, sir.
and 5 carbon monoxide, each one donates 2 electrons. So 5 into 2, so it is 1 short of 36. Now,
Yes.
when each manganese gives an electron, I have put a cross for the second manganese and a dot for this manganese. So when it donates an electron to form a metal-metal bond, then you count both the electrons around each manganese. So now manganese has 24 electrons. Manganese has given 1 electron, so remaining 24 plus 10 plus these 2 electrons. So it becomes 36.
36.
So by forming a metal-metal bond, the 1 electron loss can be regained. And as a result, it exists. Similarly, COCO4 does not exist. You have done last time that CO27
And plus 35. 35.
so it will not exist. It exists as COCO4 minus, or it can form a
Time.
it can form a dimer. As a result, the 1 electron which was short can be minimum, can be compensated. Okay. Now in metal carbonyl, the stability of the metal carbonyl is due to back bonding from metal to carbon monoxide. So, this is the first act of the carbon of the carbon monoxide donates a pair of electrons to the metal, and then the metal gives the electron to carbon monoxide. And this back donation is more important than the acceptance, because carbon monoxide is a poor donor of electron. So the stability arises due to back bonding. Okay?
Yes. Yes.
Now, when metal gives electron back to carbon monoxide molecule, where the electron will enter. So, you have done molecular orbital theory?
Yes, sir. Yes.
Use molecular orbital theory and find out which orbital is vacant where the metal electron can enter into carbon monoxide molecule.
Bias.
There are three p orbitals, px, py, pz, and only one can form a sigma bond. The other two forms a pi. And those two pi orbitals have equal energy. That's why I have drawn as two lines with equal level. And equal level means equal energy. Now carbon monoxide, if we look at the number of valence electrons, carbon has 4, oxygen is 6, 10 valence electrons. Okay?
Yes, sir.
Carbon is a 14th subgroup. 14th you will ignore 1, that means 4. And oxygen is a 16th subgroup, so you ignore 1, 6. So 6 plus 4, 10. Which is isoelectronic with nitrogen?
Yes.
So what is valid for nitrogen is valid for carbon monoxide.
Yes.
So when I put the valence electron, I start from 2s sigma, not from 1s sigma. I'm not taking the total number of electrons, I'm taking the valence electron. So when I take the valence electron, I ignore this. Then 2, 4, 8 to 10. Okay? Now if you take the total number of electrons, if you take total number of electrons, carbon has atomic number 6, oxygen has atomic number 8, 14 electrons.
Yes.
Then I start from 1s sigma star. So when I take the total electron, I start from 1s. When I start from valence electron, I start from 2s.
Yes.
Now you see that where you end 10 electrons, 2, 4, 8, 10. So the immediate, the lowest unoccupied molecular orbital, that is the vacant orbital, the lowest pi star. So the metal electron will enter into antibonding orbital.
Yes.
Star means antibond.
Yes.
Now bond order.
3.
Bond order is bonding minus antibonding by 2.
3. Yes.
So before accepting the electron from the metal, its bond order was 3.
Yes.
But when the metal electron comes, what will be the effect on the bond order?
Decrease by 0.5.
Increased by half.
It will decrease.
Yes, sir.
It will decrease. How much?
Yes.
How much decrease? That will depend upon how much electron has come from the metal.
Yes.
Yes.
So now that say now the role of the metal is a donor. At first it accepted the electron, so it was an acceptor. Then it donates electron to carbon monoxide, so its role is as a donor. When it will be a better donor? When the metal will be a better donor of electrons. When the metal is electron rich.
Yes, sir. Yes.
When the metal will be electron rich, when it is in a low oxidation state.
Yes.
Yes.
So zero, negative, they are in a favorable situation to give electron back to carbon monoxide.
Yes.
So more the electron comes from the metal, lower will be the CO bond order.
Yes.
Yes.
Is it clear?
Yes, sir.
Now you have to tell me two years back in JE they asked this question, that what will be the CO bond order in you have to give me the order of CO bond order from the lowest to the highest. Where the CO bond order will be the lowest and where the CO bond order will be highest.
2, 4, 3, 1.
Huh?
1, 3, 4, 2. 2 will be. Yes.
Lowest?
1.
Lowest is second. Lowest is 2. Lowest is 2.
Lowest is 2. Then
4. 3.
Then
3. 5.
so you got it right. Concept is, I told you, metal, more negative oxidation state the metal is, more electron is present in the metal. As a result, it is a better donor of electrons. Higher the positive oxidation state, higher is the electron deficiency of the metal. If the metal is electron deficient, how can it be a donor of electron? So, this case, the donation from metal to carbon monoxide will be least. As a result, the CO bond order will be highest. And where the metal has the most negative oxidation state, there the metal is most electron rich, so it will be most efficient donor of electrons. As a result, CO bond order will decrease to a maximum level. Is it clear?
Yes.
Have all of you understood what I said? So the concept is very simple. A poor man cannot be a donor, a rich man can be a donor. So this is a concept. So this is simply a concept of that. I have given you how to calculate the spin-only magnetic moment. When an electron rotates along the orbit, what happens? Electron is a charged particle.
Yes.
So when it rotates, it creates a magnetic field. Any charged particle, when it rotates, it creates a magnetic field, and that is called orbital magnetic moment. The magnetic moment which is arising due to orbital motion of the electron. Electron being charged particle, so there will be a magnetic moment will be created,
Yes, sir.
Yes.
and at the same time the electron is spinning also in its own axis. So it is rotating and also at the same time spinning. Just like a top, it spins. So due to the spinning motion of the electron, that magnetic moment will be created. And that is called spin magnetic moment. Now in your syllabus, only spin-only magnetic moment is included and not the orbital magnetic moment. So how do you calculate the spin-only magnetic moment? I've given you earlier or not?
No, sir.
So how to calculate the spin-only magnetic moment? By knowing the value of n. What is n? N is the number of electrons. That's all. So you know what is Bohr magneton? That is a unit. Bohr magneton is equal to EH by 4 pi m mass of electron. Charge, electronic charge, 1.6 10 to the power minus 19 coulomb. H is a Planck's constant. Okay? 6.62 by 10 to the power minus 34. And mass of electron is 9.31 10 to the power minus
31 kg.
kilogram.
Yes.
So if I know the number of unpaired electrons, I can calculate what will be the magnetic moment due to the spinning motion. That is why this formula is called spin-only formula. So the spin-only formula means that it helps you to calculate the magnetic moment due to spinning motion of the electron. Okay?
Yes. Yes, sir.
electron or electrons. Calculate mu s for nickel tetracarbonyl, iron pentacarbonyl, and chromium hexacarbonyl. You can see that carbon monoxide does not have any unpaired electron. There is a lone pair on carbon, there is a lone pair on oxygen. Okay? Can you see that?
Yes.
You can see. Okay. If I stand here, can you see?
No.
Okay. So you may not see me, but you can see there.
Yes.
So the magnetic moment will arise from the metal, not from the carbon monoxide. Okay? Can now calculate the mu s value for this three.
Yes, sir.
Can you tell me what is the value here?
Root 15.
Root
15.
50. How do you get root 50?
So number of unpaired electrons in nickel is 3.
2 electrons. 2.8.
Huh?
2 root 2 pm.
What is nickel electronic configuration?
3D 4s2.
4s2.
Iron
3D6 4s2. 3D5 4s1.
So then you tell me, how do you put 50 for nickel?
No, sir. Mistake.
2 root 2.
2 root 2.
2 root 2. What? Okay. So you said root 8. 2 root 2 is root 8.
Yes.
2 3.
Root 3.
3.
Root 3.
No sir.
Only 2.
Root of 24. Root of 24.
24.
You have 5 orbitals.
4 unpaired electrons.
Okay?
Yes.
Yes.
This one?
Root 48.
Yes.
But all are wrong. All are wrong. All are 0. Diamagnetic. There is no unpaired electron in any one of them. So why? Intentionally I asked you to calculate. Because if you have a shock, you will remember that yes, it was wrong. For metal carbonyl, write down, for metal carbonyl, transfer the S electron to D, transfer the S electron to D and pair all the electrons. So, when I transfer the S electron to D, this becomes 4s0, 310 4s0. All electrons are paired. Five orbitals, 10 electrons, all are paired. So it will be diamagnetic. Transfer the S electron to D. Becomes 3d6. It becomes diamagnetic.
So, but why will it means why are electrons filled in three of them?
I will tell you why. Just
Yes.
step by step. Iron transfers the S electron to D, so it becomes 3d8 4s0. So all are diamond. Now the question is, why, you ask me, why I have to transfer the S electron to D? I have given you the shape. Nickel tetracarbonyl is tetrahedron. If it is tetrahedron, what is the hybridization? sp3. If it is octahedral, what is the hybridization? Two possibilities, D2sp3 or sp3d. For TVP, trigonal bipyramid.
Or DSP.
Okay. Yes. Now I need a vacant d orbital. I need all these orbitals have to be vacant. How can I generate sp3, a vacant s orbital, without transferring the electron from the s to d? That is the reason. I cannot explain why experimental magnetic moment is 0. Why it is tetrahedral, I cannot explain. Because it is experimentally found that nickel tetracarbonyl has magnetic moment 0 and it is tetrahedral in shape. If it has to be tetrahedral, then the hybridization has to be sp3. And if it is sp3, I need a vacant s orbital and I need vacant 3p orbital.
Yes.
P orbitals are vacant. There is no electron in the p orbital in the metal, but there were electrons in the s orbital. So in order to generate a vacant s orbital, I transfer the electron from the s to d. And then S start pairing the electrons. The group which accepts the electron from the metal, they always provide the pairing energy. So the electron gets paired. So carbon monoxide since it is an accepted type of molecule, it accepts the electron from the metal, so its interaction with the metal is strong. As a result, it provides a pairing energy which helps all the electrons to get paired. And that gives me the experimentally determined value. Experimentally, all were found to be diamagnetic. If it is diamagnetic, that means there is no unpaired electron present in the molecule. So unless I transfer the S electron to D and pair all the electrons, I cannot generate diamagnetism. And that is the reason why I said transfer the electron from S to D. I cannot predict the shape unless I have a vacant S orbital. Remember very carefully, so far they are not asked the spin-only magnetic moment for metal carbon. Okay, now you can see yourself that it could give a very wrong value unless you follow what I said now, just now. So, I will not have the proper hybridization, I will not have the proper magnetic moment, I will not have the proper shape unless I transfer the S electron to D and pair all the electrons. Okay? Now you see, in chromium hexacarbonate, how many d orbitals I require?
Two.
So, when chromium had 3d5 4s1,
Yes.
so chromium becomes 3d6 4s0 when I transfer the electron from S to D,
Yes.
and then I pair all the electrons. I can pair them in 3 orbitals. Now I have 2 vacant d orbitals available for D2.
Yes.
So now you see that unless I do that, I cannot get D2sp3 hybridization. And to be octahedral, it has to be either D2sp3 or sp3d. If you have lower energy d orbital available, it will always be D2sp3, and if it is not, then it will be sp3d.
Yes.
Did you mention, did I discuss with you the color?
Yes.
The color.
Yes.
Transition elements.
Transition element color, have we discussed?
No, sir.
Transition elements, they show color. Metal ions are colored. Metal compounds are colored. So the transition metal ions show color as well as their compounds show color. So the color will be exhibited by metal ions having D1 to D9 configuration. So the metal ion which has 1, 2, 3, 4, 5, 6, 7, 8, 9, they will be colored. D0 and D10 will be colorless. The color is due to TD transition. So when I transfer an electron, a d electron from lower energy to higher energy d orbital, I have to do some work. Since I am transferring a d electron from a lower energy to the higher energy orbital, I need some energy input to do that work. So when part of the energy of the visible light is absorbed to transfer the electron from lower energy to higher energy orbital, the remaining part of the visible light is transmitted, and that is responsible for the color. So the color which we see is due to the transmitted portion of the visible light, not the portion which is absorbed. The portion which is not absorbed, that gives rise to the different shade of color. Write down quickly. I told you that only a portion of the visible light is absorbed to transfer an electron from lower to the higher energy orbital. The transmitted light is responsible for the color. So you know the visible light Vibgeo?
Yes, sir.
Okay. Violet, indigo, blue, green, yellow, orange, red. Okay. Write down.
Excuse me, sir. So this dt transition which you told, so that two different d orbitals, they are of the same shell or they are like different shell?
Same shape. The color cannot be understood by a box diagram. Because box diagram gives you an impression that all orbitals are equal energy. It is not so. Depending on the geometry, this 5d orbitals will split into different components. If it is octahedral, so you see the 5d orbitals, which were equal energy, now they split into two components, two groups. The lower energy, there are 3 orbitals. The higher energy, there are 2 orbitals with equal energy. And when you absorb light, the electron is transferred from the lower to the higher. So only the metal ion in the gaseous state, the d orbitals have equal energy.
Yes.
But when they adopt a definite configuration, molecule, structure, then the d orbitals split into different components. Now you can see that violet portion of the visible light is absorbed. What the color you observed is yellow green. When indigo, the 420 to 440 nanometer corresponds to indigo of the visible light.
Yes.
Then the color observed is yellow. So the different shade of color is due to different portion of the visible light being absorbed. To carry out this one, to transfer an electron from one group of d orbital to another group of d orbital. And that is why we said dd transition. So if you don't have a d electron, you cannot transfer an electron, so d0 will be colorless.
Yes.
And d10, since all the orbitals are doubly of 5, so no orbital can accept more than 2 electrons. So how can I transfer an electron when all orbitals are doubly of 5? So dd transition is not possible. For d0 and d10. So when d orbitals are partially filled, that is 1 to 9, then the color will be observed. Okay? But
Yes.
it will show color but not intense color. The intensity of the color will not be very high. It will be color. Copper sulfate is blue. Chromic sulfate is green. Nickel chloride is green. They are color, but not strongly colored. Now, Have you written all this?
Yes, sir.
Yes.
Can I rub it?
Yes, sir.
Now, if you have okay? They are representative, they are non-metals or metalloids. But they are metals. Now, what is the oxidation state of copper in cuprous oxide?
+1.
What is the electronic configuration of copper plus 1?
3D10.
480.
Then why should it show color? If it is 3D10, why should it show color? It is red color. Potassium permanganate. What is the oxidation state of manganese?
+7.
What is the electronic configuration of manganese plus 7?
3D04S0.
What is the oxidation state of chromium?
+6.
What is the electronic configuration?
3D04S0.
So I said, in order to show color, D1 to D9 should show color. But you see, permanganate, everybody knows permanganate solution is purple. Potassium chromate is yellow color. Have you seen potassium dichromate? Have you seen potassium?
Yes.
What is the color of potassium dichromate?
Orange.
Orange color. What is the oxidation state of chromium dichromate?
+6. +6.
So, mercury, what is the oxidation state of mercury?
+2.
3D10. 5D10.
5D10.
Yes.
What is the oxidation state of cadmium?
+2.
What is the electronic configuration?
4D10.
There is no arsenic, antimony, there is no d orbital. So, they also show color. Antimony sulfide is orange, arsenic sulfide is yellow. All these where you don't have, where you have D0, where you have D10 and where you don't have D but still shows color, they are all due to charge transfer. That means an electron is given from oxygen or sulfur to the metal. And that transfer of electron is called charge transfer. That is responsible for color, for D0, for D10, and for representative element compounds. Now I said that they will show color, but not intense color for D1 to D9. For example, if you take a ferric salt, ferric chloride, and you add ammonium thiocyanate or potassium thiocyanate. When you go to lab next time, when you go to your laboratory, you do this experiment. Take a ferric salt and add ammonium thiocyanate or potassium thiocyanate. You will see I have written a blood red color. I have not written red colors. I have written blood red color. What is meant by blood? Intense. So I said that if you see a very intense color, even with for D1 to D9, if they show intense color, then that is due to charge transfer, not due to DD. If they show color, DD, but very strong color, charge transfer. If you take a ferric salt and add potassium ferrocyanide, you get a deep blue color. And the word deep, as soon as you write the word deep, that means it has to be charged down. Okay?
Yes, sir.
So what we can say about color? That in order to show color, the transition metal ion should have D1 to D9 configuration.
Yes.
If D0 and D10 show color, then the color has to be due to charge transfer.
Yes. Yes.
If between D1 to D9, if the metal ion shows intense color, then it has to be also charged. Okay, now transition metals metal compounds, transition metals, they are used as catalysts.